Got it. Sure. Cool. Great, great, great. We'll let everybody get settled in. Oh, let me not swipe away from. Yep. So the reason that we're installing this package is because it has a bunch of time series data in it. What's time series data? Well, you came to the right lecture. So what we're going to be going over today is we're going to be going over time series. It's probably something that you've heard a bunch of times, especially if you have any, even a passing interest in finance. You've probably heard the word time series. So we'll be going over that today. We'll be talking about what a time series is. But first things first, as I said before, we've got to install some packages. So I want you guys to do this first because we'll be talking about some, essentially the introduction to the lecture. And this might take a second, so it'd be good to essentially go and install the package now. All you'll have to do is just uncomment these two lines, 17 and 18 in the Intro to Time Series lecture code markdown, and they should install great. Obviously, you may also need to install some of these other packages if you haven't installed them already.
So is this whole lecture in R?
This whole lecture will be in R, yes. All right. And this is for this week. Okay, great. Cool. And so while that is happening, let's do that attendance. So we'll get all the folks online first. Cool. Awesome. So Alex. Thank you. Caroline. Perfect. Chad. Thank you. Joydeep. Layal. Thank you. Michelle. Monica. Monica is not here yet. And Stefan. And no, Stefan. And there's Monica. Perfect. We'll call that a here. And hopefully Stefan will be joining us in just a moment. Did I just put these at the back? That's kind of what that looks like. Great, great, great. Cool. Great. So just for anybody who's just joining us, we'll want to go to the lecture code first, and we'll want to install these packages. Easy enough. You just comment out the line, you'll run them together, and it should install the packages just fine. Cool. And so with that, we can finally start.
Sam, which lines we on comment again?
We want to uncomment lines 17 and 18.
Thank you.
The one in the packages, our packages. Cool. Great. So this is an introduction to time series. We're going to cover a lot of stuff today. There's going to be some complicated math, and I'm going to try to make it as easy as possible for everybody. It's going to be cool. It's going to be exciting. We're going to do some predictions by the end of it and also know essentially how to explain what a time series is and a little bit about just the nitty-gritty of the rules of making a time series, specifically for the ARIMA process, the SARIMA process. And we'll go over what that acronym actually stands for in just a second. But first, let's talk about today's objectives for the lecture. Today's objectives for the lecture are to learn what a time series is and explain it. Seems pretty good, like a pretty good first goal for our introduction to time series lecture. Our second goal will be to interpret the autocorrelation function and the partial autocorrelation function and their graphs. So correlation, very important for machine learning, especially in linear models. Autocorrelation, as we'll see, will be the bread and butter for how we figure out how to turn a single column of data with maybe even as low as 150 observations into something very powerful and very meaningful in terms of predictive power. We want to be able to explain to a non-technical person the seasonal autoregressive integrated moving average model. And boy, is that a mouthful, so we call it SARIMA. We'll go over each of the individual parts of the SARIMA model. It's actually broken up into 3 parts, and then there's like an extra seasonal part. Technically 6 parts, but it's easier to think of it as the ARIMA and then the seasonal part. We'll go over each of the individual models, which are the autoregressive model, AR, the differencing, which stands for I, and I'll go over a little bit later why it is called integrated and not differencing, and then the moving average part. The S stands for the seasonal component. But don't worry, you don't have to memorize that now. We'll say it a bunch more times throughout the lecture. So hopefully by then it'll just have drilled its way into your skull. You'll never forget it. And lastly, our last goal, most importantly at all, we're going to actually use it. We're going to actually use it to do something. And that something will be prediction. So hopefully aren't too many questions, or the questions that you will have will be solved very quickly as we move through the lecture today. And now that we've talked about goals, we can talk about what the lecture is actually going to look like. So here is our outline for today. We are going to start simple and define a time series. We're then going to talk about what a stochastic process is. You've probably already talked a little bit about stochastic processes. Gradient descent is one of them. Stationarity, this is essentially the mechanic of time series. This stationarity attribute that we would like the data to have will be the most important thing as we move forward, at least with the SARIMA models. As I said before, the ARIMA model is actually broken out into 3 sections because it is 3 different models. It is an ensemble model. We have a moving average model of order Q. We have an autoregressive model of order P. And we have differencing, which is called integrated when we put all of the words together. And then lastly, we'll go from the whole model all together to all of the pieces of the model with their seasonal parts. So there's a reason why I said it's not really 3 parts. It's kind of 3 plus the seasonal, which makes 6 parts. So with ARIMA, we have our 3 hyperparameters, each corresponding to one of our parts that we'll go over in 4, 5, and 6. And then for seasonal, we'll have the same 3 and then an additional 3 that are the seasonal terms. And so that's all confusing. We'll get to it in just a second. First things first, what is a time series? And so the first thing that I want us to do today is, I didn't tap twice, right? No, okay. Is we want to maybe motivate this with an example. And so the example that I would like everybody to think about at the beginning of class today will be every day at work, you go and buy lunch at your favorite lunch spot. And we essentially are going to try to make an equation that dictates how much money is in our bank account at the beginning of day T. So here we have a couple of values to keep in mind. We have T, a specific day in our data. We have X sub T, which is the money in our bank account at the beginning of day T. And then we have Z sub T, which is how much money we spent or will spend on lunch that day. So we can assume Z of T is in the normal distribution, and for some mean and standard deviation, mu and sigma squared. This will become obvious why we do this in a little bit, but for right now, let's just assume this, and it kind of makes sense, right? You go to lunch, you spend about $10 on lunch each day. Sometimes you buy the soda, sometimes you buy the bag of chips, sometimes you don't, you just get the sandwich, right? And so we're kind of hovering around that central value with a little bit of standard deviation, right? Also note that we would be able to write the cost of yesterday's lunch as Z sub T minus 1 if today is day T. So the question is, can we write an equation for how much money we will have in our bank account at the beginning of day T? And so I'll give you guys about 2 minutes, 2-3 minutes in order to do that, and we can drop the answers in the Slack channel. And I'm gonna grab a water, which I forgot to do at the beginning of lecture. Give you a last 30 seconds, counting down on the clock. And if you could please drop whatever you got in the Slack channel. Ooh. No, I'm giving away my answers. Anyone? my kingdom for a single response in the chat. A whole kingdom. And it looks like Chad has got it. Cool. So Chad has given us a wonderful equation, which is essentially the same as the one on the slides. So we'll go over to the slides so everybody can see it a little nicer over there. And that's the other, yes, okay. Cool. So we'll just write a little extra. -1. Just like that. Perfect. And so we're able to put the equation together. And the idea is that we have some value, right? X sub t, which is the amount of money in our bank account, which is given by, dictated by the equation, the money in our bank account at the beginning of yesterday, plus whatever we spent on lunch. And we can think of whatever we spent on lunch in this case as a negative value. Just for the future assumption that we could perhaps create an even more complicated model that also had some kind of idea about a constant daily addition to our bank account as well for representing your pay. Cool. And
wasn't the question like what is the money in our bank, right?
At the beginning of day t, yes.
It's t minus 1 minus ct minus 1 because whatever I had in the beginning of yesterday, I spent on lunch, so I have less to do.
Yes, that's what I said, that you can have the z of t represent a negative value. So we can have z of t, the mu for z of t can be -10 with a standard deviation of 5, which is actually what we'll do in the code example. Cool. And so we'll just clear that off. And we will, for the first time today, go to the lecture code. And so I have already have all this written out. And so we'll be able to go to line 49, which will be the first part of the lecture code that we'll go over. As you can see, this is all in R. R is very good for time series. A lot of really wonderful stuff. Extra, bells and whistles involving p-value that make it much more robust than Python is, where Python is much more plug and play, and R is a little bit more building out sort of these methodical structures of testing your models and things like that. Cool. So with the first things first is we actually need to get our lunch prices. So here I'm saying for 100 days, we have our mu. The second argument in our norm is your mean. The third argument is your standard deviation. And the first is how long of a vector would you like back? So let's say we have some lunch prices. We start our bank account off, and then we look to actually add all together this recursive equation. So for the sake of making the code work, we're just going to have this be z of I, and we write a very simple for loop. This is essentially the way that you would be able to create your own random time series in R. This very, very simple for loop. So let's go over what's in the for loop. It's probably been a while since you guys have opened up the RStudio terminal. So let's make sure everybody is following along. We have our declaration. For R, you always need the argument of the for loop in parentheses, because it's essentially a function, but so for I in 2 to 100, right? and because we want to start 1 day forward from our starting day so that we can use this first balance. This will become a little bit more relevant later, but this is just a clever way of being able to add historic terms to our time series. Yeah, so we have our bank account balance on day I is equal to whatever it was yesterday, plus our negative lunch price. And so we can also make this into an actual time series object. This just means that we'll be nicely sequenced over some time period. And then finally, we can plot the time series. And as we can see, this is not a very exciting time series. This is perhaps a cautionary tale of spending a bunch of money on lunch when you're not making anything. As we can see, even starting at 400, it only takes us about 40 days to cross that negative line, which makes sense, right? We have an average of about -10 per day, standard deviation of 5. It should take about 40 days for us to spend $400. And we can see, by the end of it, we're -600, which is more or less where we would expect to be. If we were to talk about the expected value of this, by the end of it, it would be around -600, given that we started 400. Cool. Does anybody have any questions about the code, about building out the equation, recursive functions, things like that before we move forward?
Yep.
What's that?
What if we don't know the balance on the day I-1? What if we know just the starting balance?
So for the most, so you just know the starting balance?
Yeah, but like, I cannot mention.
So the idea is, right, that given some starting number, this is just some constant in this case, right? I could set this to whatever I want. In the majority of time series that you'll look at, that first value is already set. You're looking at the price of stocks over some set months. You're looking at wind speeds. You're looking at, how many people come in and out of Manhattan on a daily basis, right? Like these are all things that are representative of time series. And because they're real world examples, we don't really need to come up with this hypothetical starting value, right? The starting value already exists for us, and that's whatever value it is at the first timestamp of our time series. I don't think that answers your question, Stefan, but. Okay, so this is a purely hypothetical example, and we can make it whatever we want. When we get into more concrete examples, you'll find out that we don't ever have to choose this, and this is chosen for us. And we can talk about it more during one of the breaks if that's still a little perplexing. It's just a long lecture, and I want to make sure that we're not over time towards the end. Cool. Does anybody else have any questions?
So the TS is a projection.
The TS is an object, essentially. Like you're talking about line 59 specifically, right? Yes. So this is essentially making something into a special time series object, right? You can sort of think of it like making something into a data frame, right, in Python. It changes something about it, but underneath, it's really just like the same data. It's just in a new form. So we make the projection in the for loop, and then we turn it into this object that's better for us to put into this plot time series object. Great. So the question was, are we making the projection, so the line that we see in, oh my, the line that we see here with the line of code in line 59? And the answer is no, this is much more akin to like a type conversion or creating a new object. We do all of the math in lines 54 to 57 to generate all of the points on the line. Cool, great question. Great. Any other questions before we jump back to lecture? If not, let's get to it. We're going to jump back to these slides. We'll talk about, we've already talked about the time series of lunch spending. So we can talk about other time series as well. Other time series are things like a daily temperature in an area, a business's quarterly earnings, average rainfall per month, the width of a tree over time, and crime rate in a city in different months of the year. So does anybody have any ideas about maybe what governs a time series? Monica? Time. And let's see what our chatters have to say. Time. Yeah, exactly, Tam. Monica, Tam, you got it. And so we can define a univariate time series. We're only going to talk about univariate time series today. Multivariate time series do exist. But today, to keep things simple, we're only going to focus on one. So a univariate time series is a sequence of data over time. It's a series for time. And so we have this x1 to x capital T, where capital T is the time period and x sub t is the value at a specific timestamp, little t. And typically, these timestamps are an equal distance apart. We would very much like these timestamps to be an equal distance apart. And for the most part, we will attempt to coarse things or pick out of them, not in this lecture, but in your own time series analysis moving forward. You'll want to make things into these consistent timestamps. Great. So I'm going to leave that up for just a second more so people still have a chance to write it down if they haven't finished. But as we saw, our lunch example, right, our capital T value was 100. And so each one of these little t's was the day that we were on. So day 1, day 2, day 3, day 4, et cetera. For months, right, it could be, January, February, March, April, et cetera. And so there are typically 3 different kinds of variables in our time series. There is our endogenous variables, which are past values of the time series in question. These are also called lags. That x sub t minus 1 is a lag because it is the value previous to it, previous to the value that we are looking at when we build out our equation. The random noise is our z sub t. This is our uncertainty in our forecast. It's not maybe the most exciting uncertainty, in the lunch purchasing example where we're sort of contemplating that bag of chips or the extra soda, but it is still some amount of uncertainty in our prediction, right? We don't exactly know what the price of lunch is going to be on any given day because we're a little flexible with the things that we get. And then finally, there are exogenous variables. And these values are not in the time series in question, but have some predictive value. So for in the lunch example, this could be something as simple as, did you eat breakfast? Right? If you ate breakfast, if you're a person who eats breakfast, then there's a possibility that you might spend less on lunch that day. And if you did eat breakfast, or I'm sorry, yeah, and if you did eat breakfast, then there's a chance that you do the opposite. And so this is perhaps a simple example, but is in fact, some information contained outside of our regular time series that would have some meaningful impact in our ability to predict it. Another example of this would be, let's say we're trying to figure out how much energy is being drawn on a public power grid on any given day. We have a bunch of information, right, about the daily draws on the power grid for each day, but a good exogenous variable would probably be something like temperature. When it's really hot out, a lot of people use air conditioners, which is going to create a much higher draw on the power grid. And so if we're paying attention to that exogenous variable, then we're able to do a better prediction. We'll see that we're actually able to do some pretty good predictions with just our endogenous variable. Later on, you guys will be able to go and research on your own a little bit more about constructing those multivariate time series and folding in these exogenous variables.
This
Great.
example number 2, like random noise, that was referred about like bag of chips or can of soda with a lunch, right?
Yeah, exactly.
Random noise?
Huh?
Like in our example with the lunch,
Yes.
number 2, random noise, it will be a bag of chips or can of soda, as we told or no?
So the value of the random noise is, given by that normal distribution, right? And so that's why I said earlier, we had this thing where, and let's see if I can, it's a little low, but here we have our lunch price is in the normal distribution of mu and sigma squared, where mu here is our -10. And so it's the full price of lunch, right? The randomness comes from whether or not we buy the bag of chips or not. But it's always going to be, this z of t is going to represent the price of our lunch. And the standard deviation is the stuff that we can buy or not buy with our lunch.
Oh, you like me in direction. Can I go back to the slides?
Okay, sure.
So here you said exogenous, right? Number 3. You said it's like if we got a breakfast or not, right?
Sure.
Yeah. Number 2, like what it could be in our lunch example, just
It is the price of our lunch.
it is a price of our lunch, it's a random noise.
Yes.
Oh, but it's like
So
always the same.
no.
No.
What? So okay. So do you know what a normal distribution is?
Kind of heard that.
Okay. So cool. So there's a normal distribution, right? And in the normal distribution, sorry, we just very quick aside because none of this lecture is going to make sense otherwise. So you have this normal distribution, right? And that's a terrible normal distribution. It's supposed to be symmetric. Here, this middle value in our example is -10, right? And we have a standard deviation of 5.
So sometimes it is -5, sometimes it's -16.
Yeah, or it can actually be anywhere in this range of values, right? It's just most likely to kind of be in between those two. So every time I pick in the random normal distribution, I'm kind of picking a random point, right? We're kind of here, we're here, we're here. It's just if I were to average the probability of getting all of these points together, I would get -10. Or sorry, the probability times what their value is. I'll get -10. And that's our mean. And so this is still a random value, right? This is random noise. It's just centered around something that's not 0.
Mhm.
Does that make sense, Simone?
Kind of.
So yeah, this is random in the sense that, we're randomly picking from this normal distribution. Cool. Yeah, we can go over normal distributions perhaps during the first break more. Yeah. Okay. Yeah, just think of it like, given a certain thing, we have typically an average value of what it might be, and then we have some wiggle room. And all of those things together are the random noise. Cool. So you guys have done a bunch of machine learning. This is actually the last lecture in the first part of the the first machine learning section. So you may be asking yourself at this point, why are we doing time series instead of this other thing that we've just spent, weeks learning? Well, there's some good reasons. So really the most important one, I would say, the two most important ones are probably 1 and 3. It being easy to explain and giving us some insight is a very nice benefit of the simplicity of the time series. But most importantly, it works really well with low dimensional and sparse data. So that's what I was saying before. In a time series, there's a real possibility that you only have like 150 observations, and there's only one column, and the column is the price of your stock. Like, that's not a lot. And as we've learned from simple linear regression and things like that, this is really, really hard to model with machine learning. You essentially just have a bunch of techniques that allow you to regress to the mean without really doing anything a little bit more insightful than what we'll implement here with the autoregressive function. And then the third point is this accounts for growing uncertainty as we move away from our current time. And so in the typical example with machine learning, we have, and we can put on our linear regressions and our other types of regression, a confidence band, which will essentially tell us how confident am I that the values land in this area outside of my regression line. In typical machine learning, as we predict further and further away from our now, we keep essentially the same confidence band. However, with time series, we really do account very well for the growing uncertainty, because as we'll see, the majority of these time series equations are built recursively. So as we move away from our current time, from our today, let's say we're using the last 3 days, thinking about it, we're essentially starting to use only synthetic data as we move forward. If we move too far from our current time, we will only be using synthetic data. And so that might be a little confusing, but we'll go over it more when we talk about the autoregressive part of the ARIMA model, because that is the part that cares about historical terms. And so we'll be able to see firsthand this kind of, we're just using purely synthetic data, right? Do people have questions about that? I feel like I got a bunch of confused looks about the synthetic data from the audience.
No, synthetic data will be like not the real data, but the one that we predicted.
Yeah, exactly, right? Because if we have some equation, x of t, as we saw before, t minus 1 plus the z of t, let's say I only know t up to 100 in our lunch example as before. Once I get to 101, then this x of t is synthetic, right? It's not a value that exists yet in my time series. I'm adding a new value. And then the second time, I'll be using that synthetic value to predict again. And we'll see why this is a huge problem in just a second. Was that a question of the back file? No, I thought I saw you raise your hand. It can either be Z or ZT minus 1. It doesn't really matter. Because the indexer, because the two terms aren't directly related.
We are predicting like XT, which is like today how much money I have to spend.
Mhm.
So shouldn't it be the money I spent yesterday and minus the money I have?
Yes, you can do it that way. There is also, saying essentially the end of day as well. Where-
XT can be in the beginning of the day.
Yeah, exactly. A lot of the time, it's really just to keep all of the indexing nice between all of the different values. Cool. So most importantly, right, just to recap, we work very well with this low dimensional and sparse data, as we'll see, and we have a really good account for growing uncertainty as we move forward in time. Cool. So this is the time series of the Johnson & Johnson quarterly stock return, or I believe just one stock, or yeah, earning per share. And so this is a time series, right? We have indexed over quarters. We can see it has this big movement and trend up. We'll see in a little bit that this trend is very bad and we don't want it. And we'll in fact take it out of the data itself in order to do predictions on the data. We also have wind speed. This one is through the month of May, or May to July. My index is a little messed up, but that's okay. And as we can see, this is not really trended at all, right? We're essentially pretty evenly around this 10 knots, and we just have some randomness to it. These kind of time series we like very much. These are the kinds of time series that we won't have to do too much to it in order to do our analysis on. And so with that in mind, let's introduce our star players for today. These are going to be our theoretical heavyweights and are going to be very important for us to understand what we do and do not want from time series. So we see here, this is the white noise distribution, also known as the random normal distribution, because it is essentially just x sub t equals z sub t. And so we say, and we have this z sub t in this specific case equal, or in the normal distribution with mean 0, so we're centered around 0, and a standard deviation of 1. This is your standard normal distribution. And the thing that we'll find out that we like so much about it is that randomness, is the fact that it is essentially white noise. There is no relationship between any of these points in the data. Each time we get a new xt, we get a new value that is only related to the last in the sense that they are both from the normal distribution. Cool. And so our second theoretical example will be the random walk distribution. If you've studied math before, you've probably heard about this one. Essentially, the idea is that we have a starting position. In this case, we'll have the starting position be 0. And at every time step, we walk in some random direction, a random amount. And so here, we can only walk in 2 directions. We can either walk positive or negative. And we demonstrate this equation by saying that wherever I was last, update my position by some number from the random normal distribution, and then that's my new position. So all of these values are really heavily related to one another, right? Because just like in real life, I can't magically teleport somewhere without essentially, or well, I can't, without any consideration. I probably can't teleport ever. I don't think technology is there yet. But for me to get from this side of the room to that side of the room, I need to walk over there, right? And at each time step, I am updating my position, which brings me closer to being able to actually stand here. And we can kind of see that in the graph itself, where we have this movement where we're essentially moving around, right? And we can see that this leads to kind of trend in our graph. We have these periods where we're going down. We have these periods where we're going up, down and up and down and up. And it's really because we have this relationship here with this x t minus 1. And we'll see that this is the type that we don't like. These are the types of time series with trend and other sorts of meandering values like this are the ones that we really do not like. We will try to do our best to transform this random walk time series into this white noise distribution. And that will be sort of the underlying mechanic that allows us to do this time series analysis. But enough about, yes, Stefan.
Why is the white noise better than that?
We will go over it. Just think about it for right now, that this one, when we see lines like this, we'll need to do some stuff to it in order to make it into this.
All right, the random walk, my position depends on the previous one, right?
Yes.
How about here?
It does not, right?
Does not?
Because x sub t equals z sub t. And z sub t is just a value from the normal distribution. So at z sub 1, I pick a value from the normal distribution. At z sub 2, I pick another value from the normal distribution. At z sub 3, I pick a third value from the normal distribution without any regard to the previous values that I've selected. Because there is no x term here recursively. Cool. And so, yes, I know you're all like, what does Sam mean about these random walk equations being bad? But the thing to think about is when we have this trend, when it's not all just randomly distributed, that's when we start to have some issues with some of our assumptions. So before we can talk about our assumptions, we have to talk about what a stochastic process is. So a stochastic process is a random process. And so these equations that I've been putting up on the board are all stochastic processes because the thing underlying them, right, this z of t being in the normal distribution, is random. Unless we set our seed to the same thing, we're not going to get the same results every time we run one of these. We're going to get new values. And that's what I'm trying to represent here. Sure, it may look like, Jackson Pollock or something, but the idea here is that if I were to run this white noise formula 4 times, I get 4 different graphs. And we can kind of see that here. I've graphed 4 graphs at 4 different colors, all on top of one another. However, the thing is here, we're kind of still all in the same space, right? Even as I made all 4 of these, I'm still pretty well bounded between my -3 and 3. We still have our mean around 0, and that's because this is a random normal distribution. And so we kind of have an understanding about how this is going to work. However, With our random walk formula, that's no longer the case, right? We now have this thing where when I plot 4 of the random walk formulas or random walk graphs on the same graph, we get wildly different values, right? And so with this in mind, we can start to think a little bit more about why we like the random noise more than this one. Because what we're soon going to talk about is that essentially all of the processes of time series that we want to look at are stochastic processes. And from the graphs that we just saw, we can see that the equations can make wildly different values depending on what's run. And so this starts to give us kind of an issue, right? If all of this real world data is essentially made from these random processes, these stochastic values, then how are we ever going to reverse engineer them, right? Because with this, it's a little hard because at any time we'd only have one of these representations. And these representations can be so wildly different that it becomes difficult to predict them. However, if we can get our data to start looking like this, then we know kind of what the predictions are going to look like, right? We kind of understand what the realizations, as we like to call them, of whatever underlying equation dictates your stocks, your lunch price, your other things like that, because we are sort of in this space that we understand, which is the white noise distribution or the random normal distribution. So we only have one realization of the underlying equation, right? You only have one look at stock price from the last 100 days. You know, you can do your simulations, your things like that in order to generate more data. But in reality, there's only one realization of that last 100 days. So we have to introduce some more terminology in order to actually get to a place where we can meaningfully talk about how to essentially collapse this all down. Cool. So the first thing that I want to talk about is just a little review of statistics. These are things you should know, and also things people can ask you on interviews. So this is the expected value operator. The expected value operator sounds very scary and is actually just the mean. If you've never seen it written like this, I would take a moment to sort of soak this in. This is equivalent to the mean in most situations. Here we have the value x sub I for each value that we could get in our distribution from I to n times the probability of getting that value. So for a simple example of applying it to something that is kind of like, that it is essentially a mean, right? We can think about a dice, a 6-sided die. And so for each side of the dice, x sub I is 1 through 6, right? And so at each step of the process, we replace 1 and then the probability of it being 1, which is 1/6. We repeat this a bunch of times, and we get the value 3.5 as the expected value of rolling a single dice with no reroll. And if that's confusing, you should work it out. It's very easy to actually work out the expected value of a single dice with no reroll. So yeah, take a crack at it if you're confused. So this is all well and good, and this is definitely something that you should have on your radar, but the thing that we really care about here with this expected operator is that when the expected operator E is applied to X, where X is the Gaussian normal distribution with mean, mu, and standard deviation, sigma squared, the expected value is mu. This is our important result that we'll use in just a moment. We'll also talk about two different things, those being the variance operator. And here we have a very similar result from our Gaussian normal, which is essentially that this variance operator becomes sigma squared for any value of X in our distribution. So just to recap very briefly, if we have if our X is in this normal distribution and we take the expected value of it, we'll get the mean of the normal distribution. And if we take the variance of it, we'll get sigma squared, or the variance of the distribution. And this is for any value in that distribution. Cool. Let's take a 5-minute break and be back at 10:36. Hey, everybody. Time to get back at it. Hey, Bria. I'm good. How are you? You excited? You relaxed from being all done?
Yeah, I'm done, but I'm planning to polish the project which I did here.
Mm-hmm.
Once I'm finished, can I share with you whether you can give me the feedback?
Yeah, totally. Absolutely. I would love to, we could totally sit down for like half an hour or something and go over the project once you have it all,
Sure, because two of the project I think I can make some more improvement in that.
Mhm.
So once I finish, I planning to finish in a couple of days. Once I finish, I'll share.
That sounds great. Yeah, just send me an email or send it to me on Slack. Yeah, that sounds great too.
Thank you.
All right. Back at it again with the time series. Great. So we have learned the exciting result that the expected operator on the normal distribution is the mean of that normal distribution, and the variance operator on that very same normal distribution is the variance of that normal distribution. Very shocking stuff. And so once again, we'll just go over this. A stochastic process is really just a random process, and the equations can generate wildly different data depending on when we run it, meaning that they are non-deterministic, right? They're determined by randomness, not by some set values somewhere stored in the cloud. And we'll define two types of stochastic processes just up ahead, discrete and continuous. We'll show the continuous definition. Don't focus on it too much. We're just showing it for completeness. I don't think any of you are physicists, so I don't think any of you will be immediately applying continuous stochastic processes. Great. So what's a discrete stochastic process? Oh, I have a question, I think. Life is non-deterministic. Yes, life is non-deterministic as well, Tam, yes. The discrete stochastic process is a group of random variables structured as a sequence, which can be finite or infinite, and has some discrete time index, which we will refer to as x sub t. For instance, one of these discrete stochastic processes could model what a company's quarterly stock earnings would be. Why is this a discrete process? Because quarters are discrete periods of time. They are not continuous periods of time. It's quarter one for a while, and then it's quarter two. There's essentially a step in the separation of the two values. It goes from 1 to 2 to 3 to 4, back to 1. So that is a discrete stochastic process. And I'll leave this up for a second because this one's a little bit long in terms of the definition. And then nobody has to write down the one on the next slide. This is a continuous stochastic process. So my microphone's on, right? Yeah. Continuous stochastic process is a group of random variables, but instead they're indexed by a continuous variable, which we'll write as x of t. If you've been paying very close attention to my enunciation, I said something different this time. Before, I've been saying x sub t. Now I said x of t. This is a very, very small point, but an important one. It is literally different. X is a function of t, as opposed to x being indexed at some time t. X sub t means that latter one of x is indexed at some time t. Very, very kind of small, but I find it an important distinction in the language. So One of these things, and that's why I was saying that not many of you would use this, is the Poisson process. You may also know as Brownian motion, which is modeled by this continuous stochastic process. That's essentially a particle on the surface of water moving around. Not super exciting for what we're trying to do today, but still exciting nonetheless. The marvels of the physical world are many. Cool. So now we can sort of jump back and talk about these again. So these discrete stochastic processes. So we have two here. We've got our white noises, which we will once again show that these are the nice ones. They behave well. We kind of like these because we know we have some expectation, right? Some expected value of what this is going to be. Maybe that all that stuff that I was saying about expected value and variance is actually just referring to this and the fact that given the things that we said earlier about the value being the mean and the variance being the variance, then if we're allowed to get it here, then we know a bunch of information about it already because of those results we had earlier, where we know what the mean is and we know what the standard deviation is. However, in this case, we can't do that, right? Because we don't know what it is. Because if I were to look at any segment of these values and take the average of this selection of the black line right here between 0 and 200 is much different than my selection between 400 and 600. And so I don't have that same kind of information, that same kind of understanding of this distribution. And how do we actually quantify that? And so the first thing we'll do is we'll make sure we'll clear up the stochastic processes, and then we'll figure out how to actually dig deep, which will be the stationarity. So the takeaway here is that we typically have one sequence of this observed data, right? You only have one time series of whatever the stock has been for the last 100 days, whatever the temperature has been for the last 100 days, et cetera. But we want to be able to reverse engineer the properties of this generating process from this single trajectory or this single realization of the stochastic process. We call the set of all possible trajectories the ensemble. And if we wanted to specify the exact structure, we would need to know the joint distribution of the full set of random variables, which is essentially impossible in real life. This would be like knowing everything. This is the equivalent in statistics of knowing the full population, right? This is not something that ever really happens. Cool. So we have this thing that's really hard, but can we actually do something else that's kind of similar that's pretty easy? So the first thing that we have to do is we have to actually show what it means to know the full joint distribution of the random variables. So we have to rely on our expected value and variance operators. And so we have this table of E and V, right? So we're trying to figure out what our time series actually is underneath by taking these E and V values of a generic discrete stochastic process. So here we can see that because we don't know that this is from a normal distribution, we don't know anything about this at all actually. All we can say is that the expected value at the first one is kind of whatever the expected value at the first one should be. And so is the variance. And as you can see, that's really unhelpful because we don't know that, right? That's the thing we want to know. And so we've essentially, we're kind of like, phooey, seems like we've been foiled. However, let's say if this was the white noise example, then this starts to look really good. Because now we know at every single point in our discrete stochastic process what our expected value and variance should be. Meaning that we know the full joint distribution of all of the random variables in our ensemble. Because at each point, we know about where it should be and the wiggle room. And so when we have this full joint distribution out, right, we can start to talk about something and showing the stochastic, the autocovariance function, which will allow us to sort of understand this stochastic process a little bit more. So we know all of the individual distributions, right, in our previous example, because they're all essentially the same. The next question to ask, obviously, is how do they relate? And so, just like in regular statistics, we can rely on the variance and the covariance. And so, we can determine an autocovariance function, which, surprise, surprise, will lead very quickly into an autocorrelation function. And so we're essentially saying here, we want to take two timestamps, two random variables of our discrete stochastic process, and define the relationship between them as gamma of timestamp 1 versus timestamp 2. This triple equals is defined as the expected value of x sub t sub 1 minus the mean at that value. And then similarly over here, x sub t sub 2 minus the mean at that value. And so we are still dependent on each individual timestamp, and we want to generalize instead. The reason for this will be because we're attempting to turn a single column of data into the main engine of our predictor. Why do we subtract the mean? We subtract out the mean because it's supposed to be the value at x sub t minus the mean gives you just the variance, right? Or gives you at least a little bit of the variance. And we're looking at both of the variances with one another. So we're looking at how they co-vary, the covariance. Hopefully that answers your question, Tan.
T1 and T2, you have two different views. That's like two different variables.
Because they're two different timestamps, right? Because in this situation, like, right, this could be T1 and this one could be T2, right? Right, it's just two different timestamps that we picked.
But shouldn't they have the same mean?
Only if they're from here. Only if they have this kind of definition, right?
Okay.
Because in the general stochastic process, we get something that looks like this, right? And so, as we'll see in just a second, if we have this, we won't be able to transform our autocovariance function the way we like it. But with this, we will be able to. Mostly because this is essentially independent of what timestamps you pick. And as we'll see in just a little bit, it's actually more about the distance between the two timestamps. This is just like the general form. Cool. So how do we actually do that reduction? We do the reduction by proving stationarity. Stationarity is essentially our full joint distribution understander. So we have this problem, right? And our problem is that we are trying to reverse engineer a stochastic process given only one observed time series. A similar question would be, can you guess whether a coin is fair by a single toss? And the answer is no, not really, right? It would be very hard to tell by a single outcome whether or not something was fair. So we'll see that we'll want to assume stationarity because it helps us combine our current data in a way that allows us to say something very meaningful about the process underlying the time series. As we'll see, this is us applying the autocovariance function. We'll first introduce the essentially impossible version of stationarity, the hardcore theoretical math version, which is strictly stationary. Strictly stationary, we say a stochastic process is strictly stationary if the joint distribution of x sub t to x sub t sub k is the same as the joint distribution of x sub t plus 1 or x sub t sub 1 plus tau to x sub t sub k plus tau. Tau is some shift. So tau would be like, 1 or 5 or any number essentially, as long as all of these values are still in your distribution, right? So this is crazy, right? This is essentially saying if I'm going to predict what the temperature is outside, then the joint distribution, the distribution of the values of the temperature in February need to be exactly the same as July. That's crazy, right? It's not even the same average temperature out. So often this is totally insane in terms of actually trying to do analysis like this. However, we can instead say something else. because we still want the results of this. Because our results are essentially that if our time series is strictly stationary, we get a familiar friend. We have the expected value of x sub t for all t is equal to the average, mu. And the same thing for the variance, just equal to the variance. I can show this result at the end of class, but we can also show that gamma can be reduced essentially just to the difference between the timestamps. And then we can write it instead as this tau. And so we are now talking about not only the relationship between two timestamps, we're talking about the relationship of all timestamps in that time series that are tau apart. So with tau equal to 1, I'm talking about every point in my time series that is 1 point away. So the relationship of the second point to the first point, the third point to the second point, all rolled into one number. And that's the autocovariance. And if we have autocovariance, we can make autocorrelation. And the autocorrelation is just rho of tau is defined as, surprise, surprise, it's covariance over variance. And let's relax some assumptions, and then I'll take questions after just a quick. So just wanted to put these up there for everybody's sake. And to answer Tam's question, why do we subtract from the mean? because we're essentially building covariance, right? We do the same properties, same understanding that we do when you calculate the normal covariance, where we're looking at these values around the mean. And then our correlation is that covariance over the variance between the two. Cool. Great. So we want to define weakly stationary below. And we're kind of doing this thing where we're seeing if we can put these properties on top of our graph and they behave. So weakly stationary means no change in the mean and that there is no change in the variance, right? If there's no change in the variance, then our earlier result will allow us to show that this gamma function can just be reduced to gamma of tau, and we get this nice value. And as I said before, I just want to make sure we get to lecture or get through the lecture on time. And so I will show the result of getting gamma T1, T2 to tau at the end of the lecture. Cool. So we showed the equation for gamma at the beginning. And just to add a little note at the bottom, gamma of 0 is equal to, right, the expected value here and here. Because tau is equal to 0, that means there's no distance between these timestamps, right? So they're the same timestamp. Which means that this reduces to the equation for variance. And we get the variance of x sub t equals sigma squared. And this is just pushing symbols around to get the gamma function to look like the variance function. So these are all very confusing, but what do they mean when we actually look at data, actual data? So just keep if you forget all of the symbols, if all of the symbols are washed away in your mind, the two things to remember are we have this weakly stationary when we have no change in mean and no change in variance. Cool. And so now we can start to ask the question when we see graphs, is this stationary? And so I want to give this up to you guys. Is this stationary? We've got a no, we've got a yes. Do I have another no, another yes? Ooh, yes, perfect. Actually, it is strictly stationary because we do know the full joint distribution, right?
Should it,
The Gaussian random normal is a strictly stationary series. We'll see that we'll get things to this point in order to call them weakly stationary, but this guy is the real deal.
So would you say like xt1 and xt1 plus tau should be same? So I'm assuming xt1 and xt tau are two different time distribution,
xt1.
and xt1 plus tau. Like they say.
Yeah, you're saying that like this part and this part
On the score.
are essentially the same,
Same time.
or have the same joint distribution, which is true because this, where is it? This is essentially the table of the full joint distribution, right? And so because we know that the white noise has all of these same expected values here, then we are able to say that the white noise, the random normal distribution, is strictly stationary. This is the only thing we'll run into today that's strictly stationary. And it's just really because it's a theoretical example from a distribution we understand. You could do the same thing with a lot of different distributions here, but we talked about the Gaussian normal because it's the most understandable.
We talked about like example like February, weather in February and weather in June.
Mhm.
I thought these are like two different distributions that we are looking at.
No. So what I'm talking about here, right, is when I want to talk about, the stochastic process, the full joint distribution. I'm talking about it for a specific time series, right? So it's just one, right? And what I was saying there is if we were to look at the time series, right, of predicting the temperature for the entire year, and we have, it's more of like 1 month of our time series is here and another month of our time series is here. So that's not stationary, right, in our data because we have 2 different means in different locations. Yeah, no problem, Monica. Cool, so where were we? We were here, yes. So we had just talked about strictly stationary and weakly stationary, and we have sort of come to some kind of consensus that this is this is strictly stationary, but this will be the form that we try to get to represent that we are weakly stationary, because we could definitely call this weakly stationary, right? We don't have a change in mean in any point along here, and we are neatly bounded. We have this nice bound in between 3 and -3, which essentially means that we don't have any significant change in variance. Do people see that when they look at the graph? Should I talk about this more? Should I explain it in a different way? So we can call this weakly stationary, right? It's strictly stationary by definition, but in something that's more practical to us, we want to try to build up some kind of intuitive understanding about weakly stationary. And so here we're thinking about, is there a change in mean? And we can see, we're around 0 the entire time. It's pretty good. And we're asking, is there a change in variance? So that's sort of asking, am I neatly bounded? But it's a little bit more than neatly bounded, right? Because I can be neatly bounded and I can have kind of like a bow tie shape, right? Where we pinch in the center and then flare out at the ends. And that would violate my weakly stationary because that would be a significant change in variance, right? The variance at the first section, at the widest part of the bow tie, is much more than at the thinnest part of the bow tie. And so we'll see that there are also transformations that we can do to help us make that variance constant. Okay, so is this one stationary? I see a lot of shaking heads, and you'll be shaking them right, because it is not weakly stationary. And why is it not weakly stationary? Yes, both of those are true. Just as I said before on a different example, if we take the section between 0 and 200, we take the mean, and we look at the section between 600 and 800, or maybe even 800 and 1,000, these are totally different. This is the first indicator, right, of trend, some kind of trend in your time series. And we'll need to get rid of that trend, because if we don't get rid of the trend, we actually violate this, the no change in mean. You can write out and do it for the the random walk, and you'll actually see that we don't get this nice little, we don't get this mu, we get mu times t. And additionally, we don't get the variance, we'll get the variance times t. And so that essentially means that the mean moves, and so does the variance. In this situation, we do actually have the constant mean, because when you do all the numbers out, we'll see that the mu of 0 actually cancels the term. But for our own nice, clean thinking, just remember, when you see this kind of meandering pattern, it typically means that there is some kind of trend that we need to remove from the data. And that trend violates our consistent mean and our consistent variance. Cool. Does anybody have any questions about that? Great. So what have we proved today? We've proved so far, we've defined stationarity, we've defined the white noise time series, we've defined the random walk time series. We've shown that the white noise time series, or the random normal time series, is stationary, strictly stationary even. And the random walk time series is not stationary. Additionally, you can show that the moving average model of order Q is also stationary. There is an interesting result that if we know that essentially the sum of independent variables that are randomly picked is also a stationary series, and this will become pretty important later on in the lecture, because we'll show that if we're able to set half of our equation equal to this moving average model, it means our whole equation is stationary. And it allows us to do the full powered ARIMA and SARIMA time series analysis. I understand it can be a little dissatisfying to see, a lot of, won't show it in the lecture and things like that. But this is a lot of material to cover, and also without going into, series and sequences and geometric sums and things like that and doing long proofs, we can't really show meaningfully a lot of these results. We just have to sort of take them at face value. Cool. So we're now going to talk about the first part of the model. But before we talk about the first part of the model, actually, yeah, we'll talk about the first part of the model, and then we'll jump to the code book probably after the next break. Should be coming up in probably about 10 minutes. But so the first model that we're going to be talking about is the MA part of the ARIMA model. So it's the MAQ part. The Q is with the moving average part.
Hold on. What are we doing right now?
We're talking about the individual pieces of the model now.
And this model is what?
This is part of the time series model that we're building out. The entire point of this lecture is to build towards the SARIMA, the seasonal autoregressive integrated moving average model, which is the time series model, one of the many time series model, but is the one I'm teaching you today. It's essentially like what we call our like multilinear regression.
Yeah, I just get lost like from all the.
All of the stuff previously
Uh-huh.
is motivation that allows us to get to here. Because there is no free lunch in math. That was the first graph. Yeah. And we essentially need to build out this idea of stationarity to understand why we need to turn this into this from like a mathematical point so that the hypothesis tests and stuff that we're talking about later make more sense. Yeah. Cool. So this is one part of the model. There are two other parts, but we'll talk about this one first. This is the moving average model of order Q. And so let's motivate it, as always, with a real world example. And let's say a company's daily stock value is this X sub T value, and there are daily announcements that affect the price. These daily announcements we can model as Z sub T. These are, I don't know, breaking news stories, right? They're, let's say, a quarterly earning report or something, right? It's just the day-to-day news and how it affects the kind of, perturbations, the shocks in the market. And so let's say people, have a generally short attention span, and the last 3 days only have an effect on our price. So we're able to build out this model, and we'll write it out as X sub T equals Z sub T plus this weight theta of Z sub T minus 1. So that's the one from 1 day ago. Here's the story from 2 days ago. And then here's the story from 3 days ago. And these thetas are all different weights for our function, right? Because we can essentially say something like, right, sure, the first day, everybody's like, oh, yes, I remember that so clearly. And we can have a high value for theta on the first day. But by the second day, people don't care as much. And so we go, okay, maybe we care a little bit less now. So it's only like 0.4, right? We're allowed to use these weights in the same way that we use weights for linear regression and things like that. Hmm?
What is Q?
Q is the order. So this is an MA3 model where Q equals 3. So we look 3 terms into the past with our random shock values.
We try to predict the stochastic on day number T, correct?
Yes. And so with our MA3 model, or moving average model of order 3, we have an order of 3, 1, 2, 3, in terms of us looking backwards. Cool. As we'll see with pretty much all of the models, this number refers to the order. Cool. And then just a general form for everybody, just quickly. We can see that the moving average model of order Q is Z sub T plus theta 1 Z sub T minus 1 all the way to theta Q Z sub T minus Q. Right? It's just you get as many historic lag or historic random shock terms as your Q. Cool. So we'll return to our example and we set some thetas. There are some rules to setting the thetas. And they're essentially just diminishing values. And then we'll finally, after a good amount of time, jump back to the code. But let's actually jump back to the code at 11:30, and we'll take our break 5 minutes early this time. So be back at 11:30, and then we'll go through the 3 parts of the moving average model, or sorry, the ARIMA model. We'll talk about seasonality, and then we'll wrap the whole thing up. All right. It is about that time, everybody. Time to reconvene. Cool. So welcome back, everybody. We are back in the code. We will just quickly run through a couple of things because the lecture code does have all of the stuff to generate all of the graphs and things in the slides. So we'll see here, nice little code block representing our white noise time series. We're just grabbing 100 points from the random normal distribution. We turn it into a time series and then we plot it. We got a nice label on it, everything. As you can see, you have our nice white noise. Starting at line 114, we can see how we generate the random walk function. This is exactly the same as our lunch example, except we have a different starting value, and the values for our distribution are different as well. And we can see this isn't even the same one from the one on the lecture. It's already different. So yeah. Well, those are we'll just do these just to make sure stuff later runs fine. But these are the 4 random walks. Here we have the autocorrelation and autocovariance functions. We'll talk more about these in just a bit, but essentially the way that we interact with them is very easy. We just have this ACF. We put in what type we would like, or I'm sorry, we put in our data, then we follow it by the type, and then we can add a title, labels, etc. So you have to specify covariance. The default is autocorrelation. As we'll see, this covariance number is not super useful for us. We'll see that, okay, here we have this autocovariance function that's some value at 0, and it kind of goes all the way down. This is the autocovariance function of our random walk time series. As we'll soon reveal, this is a great indicator that there is some kind of trend or carryover, and we'll see that again with the autocorrelation. This is the autocovariance of the white noise distribution. And as we see, we only have one value at 0, which makes sense because it's essentially just the deviation, right? It's just the variance. Here we'll see that a little clearer by having these values bounded, by having them be the autocorrelation instead. So here the type is correlation, and we keep our nice title. And again, our first graph is the graph of the random walk. And as we can see, we have this mysterious blue line, which will probably become very important in a couple of minutes. And we have a bunch of lines that are way above that mysterious blue line. This is essentially just the bounded version of the covariance, of the autocovariance. And it tells us that we have some kind of trend in our data. Here, we'll see the autocorrelation of the white noise distribution. The autocorrelation at 0 is always 1. By definition. And we can just to prove that I'm not a liar. When tau is 1, when tau is 0, we get gamma of 0 over 0, which is 1. And so in the autocorrelation function, we'll always have 1 at 0, to the point where some of these graphs just take it out. Cool. So here we just have the covariance correlation again, and then we have our first moving average model. Great. And so for the moving average model, it's very similar to how we created some of our other time series examples. We have our random normal distribution, we have our MA3, and then we have our thetas. And then we say essentially for I in 4 to 1,000, we're going to create this moving average time series.
So how did we choose the thetas?
You choose the thetas in some descending order based on the unit root test, which is not really something that I can cover right now, but you'll be able, you just try to pick them in descending order so that you don't have like 0.1 and then it grows really big. Yeah, it's also something that you'll be able to play around a lot, and we'll be able to later on in the lecture be able to use other things to tell us whether or not something is stationary more than just looking at it. Yeah. So here we have the actual equation written out, right? And this is just, you know, what I had written out on the lecture slide. And so we have MA3 of our time series, the third position, but we're actually overwriting the first position, right? Is equal to random shock plus something times our random shock plus something times our random shock, et cetera. And so we see we got this moving average model of order 3. And it kind of looks like the white noise model we had before, but kind of just stretched out a little bit. It's less, you know, all clumped up and randomized. And that's because we do have at least a little bit of relationship in between our terms. There's not a lot, but there is still at least a little bit. We'll actually be able to tell how many by looking at the autocorrelation plot. Here, we see the autocorrelation plot of this MA3 model, this moving average 3 model. Remember that this 0 is always going to be 1 in our autocorrelation function. And so we now have 3 lags, or 3 points, that are above our mysterious blue line. So we can start to maybe think about what we'll get when we have different orders of these moving average models. For the moving average 3 model, and we count this as significant. If it's essentially touching the blue line, you want to err on the side of this is significant. And so here we'll see that we have these 3 significant lags. And we'll go over a couple more moving average models to try to build out that connection between what the autocorrelation plot says to us and what we've built considering this moving average model. So we'll do this one. And so we're making a moving average model of order 2. Yes, Tam got it. I was hoping to show one more example, but Tam's quick on it. Yes. Tam says there are 3 lags because we are doing a moving average of 3. Why is it always 1 at 0? So we're doing, yes, that is correct. The big reveal is that the order of the moving average model is the number of significant consecutive lags in your autocorrelation plot. And just for Tam, one more time, we'll go to the slides very quickly. And Tam, this is why the autocorrelation function is always 1 at 0, because the autocorrelation function at 0 is defined as gamma of 0 over gamma of 0, and that's just 1 because the gammas cancel. I hope that answers your question.
Yeah, it does. I just had to review gamma, but I think I could do that.
Cool. So here in our second example, we have a moving average model of order 2. We'll generate it, we'll plot it. We see something very similar, right? Essentially just looks like the white noise distribution again. And then we'll see that we'll get 2 significant lags here. We have 2 consecutive significant lags because we ignore 0 because it's always 1. So it doesn't tell us anything. But here we have 1, 2 significant lags. And here is an MA4 model. And an MA4 model is going to have how many significant lags? 4 significant lags. And here we see it again. We get 4 significant lags. And you may be curious now, hey, Sam, aren't there more significant lags on this graph than just the consecutive ones at the beginning? And you would be right. However, thankfully, we don't care. So we're essentially doing a hypothesis test under the hood with the autocorrelation function called the box-Pierce test. And essentially what this is doing is telling us whether or not these are significant indicators of what's happening in the data, right? That these are significant autocorrelation numbers. So if we're above this line, we're essentially saying that yes, these 4 terms, these 4 lags, have some kind of impact on our time series. However, because the fact that we're doing a statistical test over and over and over again, we really only care about the ones at the beginning, because there's a good chance that some of these other ones later on are not actually meaningful, right? They're just essentially error. The blue line is our line of significance. If you are underneath the line of significance, James, so what does the blue line represent? The blue line represents our significance. If we are under the line of significance, that means that the autocorrelation at that point is essentially 0. It doesn't exist. 0.05. That's why I said that this is a hypothesis test under the hood, because we are essentially testing for this significance. If it's underneath this value, that means that we say, okay, we don't care. It's essentially 0. 0.05. Yes, for the most part. Yes. Yes, because it's a hypothesis test. Yeah. Yes, exactly. We'll see us use the hypothesis test in two different ways. And depending on when we're applying it, we either want the null hypothesis or we want the alternate hypothesis. Yes. We'll want the alternate hypothesis when we're checking the residuals of our model, because that will essentially say that all of these lags are 0. So there's no information left in the data, right? We've modeled all the information out of the data because our residuals are normally distributed. And then the alternative hypothesis in that case would be, no, sorry. Other way around. Alternative hypothesis is they're not all equal to 0. Sorry, I'm confusing yourself. We'll get to it when we get to it. I apologize. Cool. So just to go over it just one more time, we really only care about the consecutive lags. We see a couple of significant lags at different points. These don't bother us because we really want that consecutiveness. And we'll see that later on. We actually use one of the variables to determine the number of lags that we're going to test for significance. So in a lot of situations, we get more values than we would actually be testing. Cool. I hope that wasn't too thoroughly confusing. So we went over the moving average. And so just to show you, because these models are very, the moving average model is a little bit easier to define than the autoregressive model in terms of how the autocorrelation and covariance function interact. And so I can actually show you, this is intimidating, I understand, but the only thing that you need to take away from this is that if we look at a value of our tau that is less than the order of our model, we should get a significant lag. And if we pick a lag or a tau bigger than the order of our model, so essentially what I'm saying is, what is the covariance between, let's say for, so for, is this on? Oh, it is. Awesome. MA3, that's essentially saying gamma of 4 is going to be 0. So gamma of 4 is not going to be significant, right? Because this MA3 only takes into consideration lags from 3 steps ago, not 4. And so if we were to look at this, right, we would know that everything after 3 is not significant, and everything before 3 is significant. And this is just the math of the visual result that we saw before.
Why is that like that? Like, why we don't care about significant after?
This is the closed form of the,
formula.
yeah. So like,
Why don't we care about the significant values after? Like you said, we only care about the consecutive significant values.
because with a moving average model that isn't using the estimated ACF, this is what it equals. And that's why I said the thing earlier about doing consecutive hypothesis tests.
Can you go on?
Have you guys talked about p-hacking at all? Okay, all right. So if you do a statistical test too many times, you will get a false positive, right? You're just, we're saying something about a normal distribution in most cases with p-value, correct? And so if we sample from the normal distribution enough times, we'll get an extreme value just randomly, right? And so if we do a hypothesis test enough times, the same thing happens. We eventually will get a false positive. And you can actually try this. You can write, a for loop in R that runs 100,000 statistical tests, and you can model them, and you'll get false positives. And so with that in mind, the graph representation that we see in the code is just an estimation, right? This is just us guessing, right? This is not some solved solution, right? Because I can only get to the autocorrelation function that I just showed you, or sorry, the autocovariance function that I just showed you by knowing, oh, hello, I would like to scroll again, thank you. By knowing what the equation is. And so in this situation, we can write down that autocovariance function, right? And we can solve it, and we can say, yes, we should expect to get zeros after whatever Q is in our moving average model. However, when we are doing time series analysis in real life, we don't have these equations, right? So we can't do the same thing with the autocovariance function where we reduce it to this nice simple form. We have to do estimates. And so those estimates are displayed here, which is why we need to take these significant lags that are far out with a little bit of a grain of salt, because these are just estimations. And also, we are doing repetitive hypothesis tests. Does that make sense, Monica? Does it explain it? Okay. Cool. Yes, so this is essentially just to show that even the math says that the autocorrelation function goes to 0 after Q lags of our MAQ model. Therefore, we can determine the order of the MAQ by looking at the ACF plot and seeing where we cross under this threshold of significance for the first time. So here, right, we know that our autocorrelation at 0 is 1 because that's just gamma 0 over gamma 0. And then we have 4 significant lags, 1, 2, 3, 4. We go under our significance, so we stop there. And we say, this is probably a moving average model of order 4. Yep. Cool. And so now we will go on to talk about the autoregressive section. But does anybody have any more questions before we move on to that? Cool. So we are already familiar with one of these autoregressive models. We're familiar with the AR1 model. The AR1 model is the random walk model. So because we're so familiar about it, let's say some things. Well, we know that the AR1 model looks at one historic term, right? And so I guess we can say that, ARP looks at P historic terms when estimating the next term. We've also shown that the AR1 model isn't stationary. And so we're already kind of off on the wrong foot, right? We don't know whether or not these AR models, in the same way that we knew that the MA models were stationary, we weren't really sure if these were stationary or not. In fact, the AR1 was not stationary at all. And so we'll write out the general form of the model quickly, just to get it all up there. And we'll see that ARP is equal to X sub t, and then Z sub t plus phi of 1, X sub t minus 1, all the way to phi of p, X sub t minus p, where Z of t is in this normal distribution. And so we can think of this model as looking at the real historical values of our time series. So we're looking p days into the past, but instead of looking at random shocks, we're actually looking at the value itself. Cool. Does anybody have any questions about the historic terms, things like that? Things of that nature, how we look at it. Okay. So we'll return to our random walk example, and we'll note that phi is 1 in this case. And so with a phi of 1, we'll jump back to the notebook. And so going like, this is essentially just the same thing. It's the same code that we've seen before. We do the for loop, we create our random walk, then we plot the time series, and then we are going to plot the ACF and see if the ACF is going to tell us anything important. If you remember from earlier, I don't think the ACF was very informative because it kind of just looks like this, right? And this is what our ACF looks like for the random walk model. But it makes sense that it's like this, because how are these terms related? They're related by 1 day or 1 timestamp in general, right? So if they're related 1 day, right, and it has a coefficient of 1, then these values just kind of carry over, right? I could actually really write this X of t as X of t equals just the sum of Z of t from 0 to t. Or let's just make this the big T for notation's sake. And so if I can write it like that, then that means I'm essentially just carrying my information through, right? At every point, I have carried information from at least 1 point in my time series forward. And so all of the points are very highly correlated with one another. They have an extremely high autocorrelation. We can think about this in a physical term because in the same way of my example of walking across the room, right? I have to keep progressively taking steps towards this side of the room to end up on this side of the room. And so all of those steps leading up to me being over here are very highly related because at every point I had to take all of my other steps into consideration to figure out where I even am. So we get this really nasty, highly correlated, highly autocorrelated graph. But thankfully, there is actually a different way of looking at this. And so to jump back to the slides, we have a different way of looking at it. Is there a better way? There is. The better way is the partial autocorrelation function. And before we jump into this definition, I'll just show you why we like this so much better for these autoregressive models. So we have this, which is the autocorrelation function, and I'm about to run the partial autocorrelation function. We run the partial autocorrelation function using the same thing, but instead we say type partial. And now we have something that's way better, right? We have something that has probably about what looks like 3 significant lags. It's got 3 significant lags, when in reality it should only have 1 because it's not stationary. So this partial autocorrelation says something about what new information is being added at each step. So if my autocorrelation was taking into account all of the steps that I had taken and where I was and things like that, the partial autocorrelation really only takes into account each new step and how that information carries over to new values. So in this case, we're only getting new information every step. And because the coefficient is so high, that information carries over in a way that it sort of fools our estimate into thinking that these are also significant. Which is why I said earlier that these trends, these non-stationary time series, things like that, will cause problems for our analysis later. Right? When we're estimating these autocorrelation values, they will have errors in them if it is not stationary. We're actually not even allowed to do this investigation if it's non-stationary. Cool. So what actually is the partial autocorrelation function? So the partial autocorrelation function is for finding new information, as I said, between these lags. And so it allows us to get a better understanding of how the terms are related because we want to look for that new information. And so if no new information is added between those steps, right, then the PACF should be 0 or under our set significance level for that lag. So our AR1 should have a significant PACF at 1, but should go under significance. And as we talked about, it doesn't because it's not stationary. If we were to make it stationary, it would go under at 1. Cool. And here we have 2 nice versions of the graph. And we'll look at the partial autocorrelation function for the white noise distribution and for our random walk. We see for the white noise distribution, there is no significant partial autocorrelation, right? There's one random one here and here, but we don't really care about that, right? We want to start at the beginning and we want to look this way. And so if there's no significant lag at the start, we say, great, no significance. Here, we have the opposite, right? And note that when we generate this partial autocorrelation graph, our 0 is moved over. This is in fact our 1. And so we have our first significant lag here, representing the fact that our Z of t is the only new information that we get at every step. Does that make sense to people? No? Okay. Yeah, so, yeah.
Can you explain once again what the partial autocorrelation function is and how we got from autocorrelation to partial correlation? What is the function?
The function is pretty complicated and the derivation takes a while. I'm sorry.
What does it mean?
It just means that this is new information added. So essentially that's like, new information, right? This is talking about the ACF for these guys, right? Talk about the information carried forward, which there isn't any, right? For that one, but there is for this one, right? Because we're looking at these historic terms. And so we get the ACF that's just like the waterfall, right? Because all of the terms in this series are connected in some way.
This is where it got with the ACF.
Yes. And since it's the PACF, we are looking instead at when am I getting new information? Does new information originate 1 step previously, 2 steps previously, 3 steps previously? And so with that in mind, we're essentially only taking our information from x sub t minus 1. So all of the new information for our new value comes from this x sub t minus 1. So the 1 step behind, as we'll see when we get to higher order autoregressive functions, we'll see that when we have, an x sub t minus 1 and an x sub t minus 2, we'll have 2 significant lags because the information comes from those 2 specific places. Because if we were just to look at the autocorrelation, and we'll look at the autocorrelation for some of our higher order AR models, we'll get that kind of waterfall diagram every single time. It's just like a little graphical error. I think the function has it at 0.005, but it doesn't always show up there. Okay. So, and we can say, note the ARP model, the PACF cuts off after P lags because that's where the information is coming from. It's coming from this X sub T. Yeah. And so we'll just go back really quick. We'll do one more, but this time we're doing it with the ARIMA simulator. This will be the thing that we actually use later on to create some of our time series models. It's very simple to use. For our AR2 example, the first argument is essentially just the weights for whatever simulated model you want. And then we have just the number of values, right, that we want to generate for our time series. And so we pick our weights. For those of you that are curious, our weights are picked, so we also, once again, do not violate the unit root test. As you can see, this is pretty nice. This seems actually, quite within our reasonable bounds, right? As well as, not deviating too far from the mean. And that's because we picked nice values for our fees. And so we'll see that the ACF does this thing, but not so bad this time, right? Where this sort of echoing effect that we had with our phi of 1, right? Our coefficient of 1 with the random walk is sort of curbed a little bit, right? Because now we have a coefficient of 0.7 and then 0.2. So historic values kind of die out eventually, right? They are not just essentially summed. So here we can see the ACF is still not very helpful. It, has this big slide down. This is actually because a secret is that you can represent any AR model with an MA model of order infinity and vice versa, which is actually the reason why we can make ARIMA models at all later. But staying on topic, we have the partial ACF of this AR2 function ends up being 2 significant lags because the information comes from x sub t minus 1 and x sub t minus 2. And we'll skip some of the other examples for the sake of time, just so we make sure we get it to everything. Here are the rules specifically for AR2. They fit pretty nice. Rules get more annoying as they get more complicated. This is essentially just saying that you don't violate unit root test. Cool. So we'll see, here is one with a negative coefficient. We get, it looks really nice. And then we have some weird stuff that happens up here. But we can see our PACF still gets us the relevant information that we need, just like the ACF was getting us the relevant information that we need for the moving average part. As we see, the partial autocorrelation function cuts off, goes under our significant level after P lags for the ARP model. Therefore, if the PACF cuts off after P lags, then we most likely have an autoregressive model of order P. And so we have two of these now, right? We have the autocorrelation function, right? Will let us know what the order of the moving average part is. And then we can figure out what the autoregressive part is using the PACF. So we're pretty close to building out the ARIMA model. We've built out the AR and we've built out the MA. And now we only need to figure out what differencing or integrated means. And so from here, we'll talk about that differencing. Ugh. So more notation, I apologize. So this notation is literally just introduced to streamline one equation later. If you don't get this, then the result of this is essentially I get to set two things equal, where one of them is stationary, and we don't know if the other one is stationary. And thankfully, by equivalence, since one side of our equation is stationary, the other side of our equation will be stationary. For essentially what we're trying to do here is we're trying to remove the underlying trend. So we have to introduce two pieces of notation. We have to introduce the del operator. The del operator is short for 1 minus this giant B. What's giant B? Giant B is the backshift operator. The backshift operator is very simple to understand. It shifts you back n timestamps. And so if we're at x sub t, and I apply a backshift operator of n, backshift operator to the n, right? Essentially applying the backshift operator n times, I get x sub t minus n. And then we'll just define it so that we apply it this way. We'll show a very simple example to show how the backshift operator is used. So this is essentially us trying to use the backshift operator to detrend the autoregressive 1 model. So we have this x sub t equals x sub t minus 1 plus some random noise. We know that the random noise is stationary, right? We said at the beginning of the lecture that the random normal distribution is stationary. So if I can get this alone and have this equal the rest of my equation, this is stationary. So this stuff is going to be stationary too once I move it over. And so that's exactly what we do. We essentially just move it over. We subtract x sub t minus 1 from both sides. We then pull out the minus 1 from here. We pull out the x sub t. We get our 1 minus b. And then we get our solved form below, where we have very neatly our x sub t equaling our stationary series, right? Our random normal distribution value. And so that sounds like I've just shown you a way to take something that's not stationary and turn it into something that is stationary. And it seems like we just need to subtract all of the terms that are 1 before whatever term in our series, right? All the terms with a lag of 1. Because when I'm doing this step here at 2, right, from 1 to 2, essentially what I'm saying, right, is for my whole series, you know, from x1, x2, all the way to, you know, I don't know, like x of n, I'm subtracting essentially this way. So let's put an x of 3 there. So this is a little less confusing. Right? So from going from 1 to 2, I essentially say for my actual values, right? If this was an actual defined time series where we just had the values for it, what I'm saying is, okay, subtract every point in my data that's 1 point away from one another. So 2 subtracts 1, 3 subtracts 2, 4 subtracts 3, 5 subtracts 4, etc. And we'll see that this is a way of removing that trend from the data. Cool. Does anybody have any questions about this before I go on? Okay. And so here we'll jump back to the code for a second, but first I'll talk about what's happening, right? We're actually putting that into practice with an actual time series. So what I'm doing is I have my random walk, right, as defined by the equation that was written at the first, next to my number 1. And then we have it differenced by 1, which is essentially what I just did. A single application of the del operator. Here we see what it actually is in the code, and then we'll jump over to the code to actually look at it.
Hold on a second.
What's that, Stefan?
So go back to the slide. One slide. So here you are as explained, it's we were subtracted from each other, right? And now go to the next one. Here, this is what we subtracted from the walk, right? And we get that.
Yes, this is just all of our values plotted, right?
And then from x, we subtracted x for each point, right?
Mm-hmm.
And we got that.
Yes, and then we get that one.
Okay.
Mm-hmm. Cool. Great. So the command for differencing is very simple. The random walk, differencing the random walk function or the random walk series, we have diff, the data that you want to do the differencing on, and then the number of spaces in between your points. So as we'll see that this number will be 1 most of the time, but when we do seasonal differencing in just a little bit, we'll see this number go up a little bit to whatever your seasonality is, whether it be quarters, years, etc. So we take the differencing, we'll plot our random walk, we'll see that our random walk, now resembles our well-behaved white noise distribution. We can take the ACF now, and we'll see that the ACF looks really nice. We have one significant lag. And then we just have, we have our regular point at 0, right? Our point in the autocorrelation function at 0 is always 1. And then we'll look at the partial. And we can see that the partial is a little bit under, but for the most part is behaving pretty well. So we have about 2 significant lags, and that is more or less how it should be when you do this little extra bit of differencing. You should be able to keep your ACF, right? Your ACF should no longer look like, as we saw above, where we saw this sloping downwards, but instead looks like this nice reduced function that only has 1 significant lag. And so we can also look at our AR2 example and see if we can apply the same reasoning there, because we had the ACF that was sort of a little misbehaving. And so as you can see here, it doesn't really seem too terrible or too egregious at all. But when we actually look at the ACF, we can see that the ACF is sort of, we're gonna both. The ACF is sort of not great, right? It's still this big sloping down. But the partial ACF definitely does, tell us a little bit about the actual data. However, we can do some differencing. We see we get something, once again, a little bit nicer towards the white noise distribution. We'll get about 3 significant lags. And once again, these are just estimates, right? And as we'll show later, that these are actually going to be just guide numbers for up to how many order we'll actually use for these values. Unlike in some of the other analysis that you've looked at, right, where you go and you essentially look at the elbow of a graph or something like that to say, yes, this is the specific value. Here, we'll find out in just a little bit when we're looking at full ARIMA models, these are sort of closer to suggestions. It'll say, oh, we'll have we will have a model of at most moving average of order 3 based on our autocorrelation function. And then when we look at the partial, we'll see that the partial only has 1 significant lag at this point. And this kind of makes sense because we are, in fact, looking at models that only have AR parts. And so we will sort of lose some of this information if we're doing this on stationary AR models. So you may be asking yourself, so differencing is for removing trends, but it seems that with all of these AR models, it seems to just, kind of mess up our analysis a little bit. And you would be right, because once again, that these are only specifically AR models. And these terms of investigations are very important for looking at the combination of different factors in these models. And as we'll see further down the road, we actually try all sorts of different combinations from what the PACF and ACF actually tell us in order to build out the model. we'll also show you very quickly what it looks like when you do overdifferencing. So this looks pretty good. However, when do you know when to stop? Because this looks probably more like the white noise that we had before. So am I doing something bad here? And the answer is yes, you are. And so we can start to see a little bit of this weird alternating pattern. And we can start to see it even more significantly in the partial autocorrelation function. So the partial autocorrelation will be your big indicator that you've sort of over-differentiated. And we get this by essentially enacting the opposite thing of what we had originally. So when we had originally this autocorrelation function, right? ACF. Hello. Right? This was our original undifferentiated autocorrelation function. And we've essentially moved that relationship by differencing into the partial autocorrelation function via subtracting too many times. Because if we take the difference too many times, really what we're doing is we're just introducing a negative relationship on the values, right? Because we're essentially building out the formula every time I'm doing that. There we go. You know, the differencing of x. So if I'm doing, you know, x1, x2, so with one level of differencing, right, we might be removing trend. But with the second level of differencing, you're essentially saying x5 minus x4 minus x3 minus, or sorry, x4 minus x3. And as you build this out more and more by applying differencing repeated times, you're building this backwards relationship now. And so that's why we are able to tell in the partial autocorrelation function when we've over-differenced, because we've essentially moved the relationship that we had, right? Where we know that in the autoregressive model, the autocorrelation is very high for all the values because we're looking towards those historic values. If we over-difference too many times, we're looking at a bunch of negative historic values, right? So we're essentially building out a different autoregressive model. And so that autoregressive model gets represented here by having a bunch of negative significant lags. TLDR, if your partial ACF flips like this after having your ACF look like this, then you've done over-differencing. Yep, essentially just, you know, if you make your PACF look like this, then you over-difference. Great. So now, this is just something so I can do something fancy later. Essentially, what we can do is we can take all of these values out for our AR model and instead write it in this form where we have all of our weights as this phi of this backshift. And we have 1 minus phi of 1, b, phi of 2, b, et cetera, et cetera, et cetera. And these are subtracting because they are differencing, right? We need to move all of these values over to this side of the equation, and therefore we get negative values. Additionally, we can do the same thing with the MA side, and we can show that the MA side actually just has these plus signs, right? Because we don't have to move any of the values over. We know that given certain conditions, the MA model is stationary as long as it is what is called invertible. Cool. So we've shown some of the following results, which are the process of differencing removes trends from the time series. Therefore, we can use it to make a non-weakly stationary time series into a weakly stationary time series. We can also do differencing via linear models by fitting a linear model and looking at the residuals. This is pretty simple. Essentially, you just fit a linear model to your data, and then you subtract out the linear model. It's a slightly different kind of differencing. Cool. And the autoregressive integrated moving average model. We finally got there. We're allowed to put it all together this way. And so we'll go over a quick example of the ARIMA model, as well as talk about that statistical test that I wanted to talk about earlier that sort of allows us to get a better understanding of what's actually going on. So we have built up several different techniques. We have the MAQ. We've got the random shocks. We've got the ARP, the historical terms, right? We've got the differencing, which is the ability to remove trends in order to essentially coerce the data into this weakly stationary assumption. We can also use the linear model to do the same thing. And the answer is, the question is, can we combine these to make a more powerful model? Of course, that's the name of the section. We are able to do this. It's just there are some specific things that allow us to do this. So we can show that an ARP model can be represented by an MA infinity model if the ARP model is stationary. We can also show that the moving average of Q model can be represented by an AR infinity model if the MA model is invertible. And differencing helps us get to these conditions. And so with that in mind, we can essentially see that we sort of start with this integrated or differencing part, and then we move from there. We say, okay, Y is essentially this, difference operator applied to my X of t, which is equal to this. And if we do it right, then we get this. We're able to write this, where we essentially say, hey, we have this AR model on this side, right, that's been differenced in some way. And we're allowed to set that equal to the moving average part. And so this really isn't terribly different than what we just did with the small example, right, with our random walk. It's just, this has a little bit more notation, right? We did our differencing, we got it into this form, and then we were able to set it equal to our stationary side of the equation here. And so we know this whole thing's stationary. And therefore, we're allowed to do time series analysis. And why do I keep saying we're allowed to do it, right? Well, we're allowed to do it because of step number 3. So here is the play-by-play. This is essentially, if you don't take anything away from this lecture, take this play-by-play away. This is essentially what we'll do when we are doing time series analysis. As you'll see with the seasonal aspect of it, we really just add an extra step that allows us to check out what the seasonal MA and the seasonal AR terms are. Cool. So what are the steps? We want to look at the data. We need to see if there's a need for differencing or if the variance is varying. The second step is to then log transform the data if you need to reduce variance, and then difference to remove trend. This is known as a log return. And please do your transformation first and then do your differencing, because you will run into less errors. Yes. It's just a good old math rule of thumb. Log transfer before you take the difference. And then the Leung box test to determine if autocorrelation coefficients are significant. This is our mysterious blue line. It is the Leung box test, also known as the Box-Pierce test. And we'll be going into it in just a second. 4, which we explained during the autoregressive part, or sorry, the moving average part, the ACF shows us the order of MAQ. The PACF shows us the order of ARP. And then after we have all of those, we can build the model and we can check the AIC of the model, as well as the sum squared of errors and the Leung Q box or Leung box Q statistics. Sorry, just 1 second. And then we're actually able to predict. So I said it a bunch of times, so I have to go over it. What is the Leung box test? So we'll go to the first one. Null hypothesis. H naught is that all of the autocorrelation coefficients are equal to 0. The alternative hypothesis is that at least one of the autocorrelation coefficients are not equal to 0. They're significantly different. This is essentially very similar to the multilinear regression statistical test that says, you know, are any of my regressors, right, actually meaningful? Are any of my coefficients good? And they say either, yeah, continue with the analysis, or no, go home. And so what is it? So essentially, it is just the significance of your lag at a certain point. So here's the equation for it. And to go through the equation quickly, essentially, big T is the number of samples you have in your time series. RL is the estimated autocorrelation at lag L. And typically, we take this M number to be the natural log of T, where M represents the number of lags being tested. If we go back to our second slide, we can get a little bit more context about what the M number is, because essentially what we're saying, and which is why I was saying, you know, we only have to look at a certain number of these, we can sort of stop looking at some point, is because we're really only testing up to M correlations, right? Autocorrelations. And so if my M has a very small value, then I'm not really testing more than, you know, 10 or 20 of these values when I'm actually looking at the autocorrelation. And so when I do my Leung box test, I'm only looking and saying, hey, are at least one of our autocorrelation coefficients in the first 10 of my lags significant? And so here, to keep it nice and simple, when we are building our model, we would like to reject the null hypothesis. When we finish building the model and apply this test to our residuals, we want to reject the alternative hypothesis. So when we build the model, we want to reject the null hypothesis because we want to say that some of our autocorrelations are significant because the autocorrelations are what we build the model with. But when we finish building the model, we want to see that the residuals are normally distributed. And if they're normally distributed, we should see that none of these autocorrelations should be significant. They should all be 0. This is one-to-one equivalent with looking at your residuals in linear regression or any kind of regression in order to get an understanding of whether or not you left information on the table, so to speak. You know, like there's something still in the model that there's still something in the data that has yet to be figured out, has yet to be modeled, right? Because if there's some kind of autocorrelation in the residuals, that means that there is some kind of information stored there, which we did not capture when we built the model. Does that make sense to everybody? The comment about the residuals, I feel like, yeah, it's like pretty important for both this lecture and also linear regressions. Yeah. If you have any kind of trend in your residuals, whether it be here or in regression, right? In machine learning regression, that means that if your residuals are not normally distributed, it means that you left information in your data set because there is some kind of relationship that you can visually see in your data that still exists in the residuals. And what are the residuals? Somebody want to answer? What are residuals? Yes, exactly. They are the difference between the estimated and the actual values. So if there's some kind of trend in that difference, that means your model did not capture that information to begin with. Cool. Does that clear things up? Cool. Great. So we're going to jump over to some, we're going to skip the BJ's example and go directly to the second example so I can make sure to talk about the Surima model as well. But we can look at the BJ sales data and we can essentially just take a nice little slideshow loop through these different steps. So we have our BJ sales data. We can see that there is an obvious kind of trend. We want to apply differencing to this data. Great, we apply differencing and we say, it still kind of looks like that we have a little bit of trend in this data, right? We have these sections where we kind of go up, and we have these sections where we go down, and we go up, and we go down, et cetera. So we will double difference the data. And we start to get something that looks like this, a little bit better, a little bit better. And then finally, we will do our box test. I have the code written up here, and we'll go over it again once we go for the airport data too. It could be a little bit hard to read, but I wanted to make sure that you guys could at least copy paste it. We have box.test. We put the double difference in, comma, lag, log of the double difference of the BJ sales data. And remember that it is the length, right? Because big T at the very beginning when we were talking about that was the number of samples in our time series. So we get the significant p-value here, which essentially says that, we are able to reject our null hypothesis and say that there is a significant autocorrelation in our data. And so we are allowed to continue with our time series analysis. We'll look at the ACF and the PACF. We'll see that the ACF has our regular usual suspect at 0, and then 1 significant lag at 1. And our partial ACF has 3 significant lags. And so we difference twice. We've seen 1 significant lag in the ACF, and we've seen 3 significant lags in the PACF. So we're going to have a differencing of 2. The order of the ACF tells us Q, so we'll have Q less than or equal to 1. And then the PACF tells us P, so we'll have P less than or equal to 3. And so this is essentially what I was saying earlier, where we are checking only up to these numbers. We want to get an idea of what these should be, and then we can sort of run through a loop of all of these values in order to figure out which is the best model for this specific instance. This is very similar to grid search, right? This is essentially us grid searching over our hyperparameters. And so this is the loop. It's very big. Don't worry, we'll go over it in a little bit more detail in just a second. We get some results. The main thing to take away here is we're looking at lowest AIC score, and we're also looking for a good p-value, right? In this situation, we want to accept the null hypothesis, because accepting the null hypothesis here, after we've built the model, right, we're doing the test on the residuals, means that we didn't leave any information in our data. We can see here that I do the box test on the residuals. Cool, and then we get a kind of mad prediction, but that's okay because the non-seasonal ARIMA is not very good. The seasonal ARIMA is much better. Great. So we'll go over this all very slowly while we look at the air passengers data that starts at 460 in the code. Okay. So air passengers data. This is air passenger data from essentially the birth of commercial aviation. If you run the question mark, you'll get a nice little description. It says, you know, monthly time series in thousands, tells you where it's from, the examples, etc. You can fit ARIMA. They have a bunch of different things on it. But for right now, we'll push this off to the side. We'll go up here. Great. And we'll plot the time series. So here we have a time series that violates how many of our weak assumptions, our weakly stationary assumptions. I think it's both. Yes. So not only is the mean changing, but the variance is changing as well, right? It's fanning out as we get further up, as well as having a trend line upwards. So we need to get rid of both of these things. Remember I said before that when we see this fanning of variance, we would like to take the log transformation. After taking the log transformation, we see something that looks much better. So obviously this still has the trend, but now we have removed the fanning variance. We can then quickly plot the time series of just the difference series. And you can see this looks much better. But I would argue that there's still some kind of pattern here that we would need to deal with in some way. However, right now, we don't really understand how to deal with that. And that will be the seasonal part that we'll talk about in just a second. However, we can still take the box test, and our p-value says, you know what, go ahead, do your time series analysis. Note that I am doing this box test on the differenced AP log. So I log the data, I take the difference, and then I take the box test of that. It's not of the original data, right? And this is because we want to transform this so that it is weakly stationary to begin with. Oh. So we'll see the ACF. We have the ACF at 0, right, is always 1. We have the ACF, the first one out is just 1. And then we get this little weird thing, right? It's like, hey, wait a second. 1, if anybody noticed, my lags changed numberings. So before it used to be like, 5, 15, 30, right? And so, okay, so that's kind of weird. So we now have lag at 1. And we have a really significant lag out there. And so we might be able to think, oh, hang on a second. Maybe this is a year. And so this 1 represents 1 year because my data set is in months. And so this is what we'll find out will be our seasonal lag. But for right now, we're just going to make a really bad time series model so we can make a really good one. And so I need to get my partial as well, right? And we'll call the partial 2. We'll say there's like 2. So we've got moving average model of order 1. We've got an autoregressive model of order 2. And we got a bunch of these funky lags somewhere out here that we'll probably have to deal with later. And so we'll push that up to 3. And then we'll run the loop, and I will stop and actually go over the loop. So D is our differencing, P will be our autoregressive, Q will be our moving average, and then you can run this without this essentially, but you'll see it'll essentially just time out on certain values when you're trying to do really large time series with high orders of models. This is what's called the parsimony principle. And essentially what you do is you just add up these numbers, typically. So with this being 2, you would kind of add up this, because I added a 2 before. So, because if I run something too many times in the notebook, this result will change because I'm a different part of the same seed. And so here, we just essentially add 1 plus 3 plus 2, cool, 6. And we'll run it. And so what am I doing here? All right, what we're doing is we're making an ARIMA model. That's the first step. First step, ARIMA model. We give it the logged data, right? Because at no part in the ARIMA process did I describe ARIMA handling the log, taking the log. So we have to give it the logged data to begin with. Then we give it the order of the ARIMA section. So the order is taken as a vector, and the vector is PDQ, just like the ARIMA was set up. That creates an ARIMA model, which does a whole bunch of other things. Populates residuals, it makes some predictions based on just what the specific time series is. So we're allowed to get this residuals. The second thing that we do is we're testing the p-value. We test the p-value for the model that we just built. We're using the residuals, and we're making sure that we pick our m properly, right? Such that it is the log of the length of the residuals. We take the sum squared of errors, and then we just do a nice little concatenation for a print that says, hey, these are my variables. My AIC was this much, my SSE was this much, and my p-value is this much. And so we'll run this again. And as you can see, we want the lowest value, but what's my problem here? If we look at all of my p-values, none of my p-values are rejecting the null hypothesis, right? And so I left some significant information on the table. And as we saw before, it looked like that big old, significant lag that was out at probably around our year mark was our significant information that we left on the table. So we can see that when I really do leave stuff in the data, it's reflected in these tests. And so we now can move on to the SARIMA section. So in the SARIMA section, we'll look at this difference log data, but we'll zoom in on it a little bit. In this difference log data, we can see a seasonality pattern, right? We kind of go shoop, and then it goes down again. And then we kind of get that one tooth, bigger tooth, one tooth. It's not perfect, but there is at least some kind of repetition, right? We have these big chunky sections like that sort of repeat themselves throughout the data. And so we want to say, right, oh, interesting. Let's do some seasonal differencing. Typically, the differencing will be whatever the length of your season or period is. And so in this situation, 12 months make up a year. So our seasonality should be 1 year. And so if I know all of the points are months, then we should be able to do differencing and do differencing instead of by just one, right? We'll do the differencing of all of the values that are 12 apart. So essentially, I'm subtracting every December from every December, every March from every March, every May from every May, in order to remove or attempt to remove the individual trends that happen in each of those months.
This we can check ACF and BACF to see, let's say this much changing or
Yes,
too much.
exactly. And so we'll plot the time series of this log difference with the seasonal difference. And it's still not great. I would say it's a little funky. Right, where this is our unseasonal difference one. And this is the zoomed in seasonal difference one. And it's looking okay. It might not be perfect, but it's looking still pretty good. And so we'll actually save that to something, and then we'll plot the full time series. And so we have something where, yeah, maybe we're not having such a great time with our variance at this point, right? We're having a little bit of a squeeze, and then it kind of opens up again. But this is part of the issue with specifically, the seasonal differencing, or, just over differencing in general, using this, simple subtract one value from another. You could probably avoid some of this reduction in variance by attempting to fit a linear model and instead removing that. But we will keep on our path ahead because this will actually give us some good values. So here we see our p-value for our log seasonal difference is actually quite good. It's great. That means we can move forward with our analysis. We'll run the ACF. We'll see we get one significant lag here, and then one significant lag at 1. So what this means is we'll have one significant lag for our MA, our regular MA model, and then it will have one significant lag for our seasonal MA model. And in the same way that we wanted to count consecutive significant lags here, we want to count consecutive significant lags at the year mark. So we'll go 1, and then we can look at 2. But 2 is I believe not significant. Sorry, give me 1 second. Why did you not load in? Perfect. Okay, so this is the other function, ACF2. ACF2, better than ACF1. ACF2 essentially makes it so your ACF doesn't have the 0, and it'll plot both graphs at the same time. It also shows you more lags, and also what the lag means. I just tend to avoid it because I don't want to show too much information right at the beginning. So here we can see the wider picture. So we still have one significant lag here for our MA model. We've got one significant lag at our seasonal term. We look to our second seasonal term and we say, do we have a significant lag? The answer is no, we don't. So we say, okay, phooey with you, only one seasonal MA term and one non-seasonal MA term. And then we do the same thing for the PACF. For the PACF, we'll say, okay, let's look at the autoregressive terms. Great, we have our first autoregressive term for non-seasonal. Great, we look to the next one, we say not significant, out of here. We're only looking at one non-seasonal AR term. We look at the lag out at our seasonal mark. We say great. This lag is at our seasonal mark, and we can say one seasonal AR lag because the mark at our second seasonal lag is not significant. So to recap, the most important part of looking at these from a seasonal perspective, right? From a non-seasonal perspective, we wanted to look at consecutive lags. And we carry that idea over to the seasonal lags too, except now we're talking about consecutive seasonal lags. So you're looking at, 1, 2, 3, 4. So, if 1 and then 2 was significant, then I would have 2 seasonal AR terms. And if 1, 2, and 3 were all significant, then I would have 3 seasonal AR terms, which would represent looking back 3 calendar years in my data. Cool. Yes.
We have this significant lag number 1, right?
Yep.
That means we need to agree to that, or that's good or that's bad. It's the like,
So we have, so at the point, and which is why I try to not show any of these graphs before we get the good p-value, because this line here, 523, after you do all of your differencing and this says you have a significant p-value, that is your green light to look at the ACF plots and to start writing down numbers about what the order of your ARIMA or SARIMA model should be.
okay, here my p-value is good, right?
Yes.
So let's look to the plot.
As in like the plot of the time series or this plot?
Which one is supposed to look at?
We were supposed to look at this one at this point.
So significant plot 1, right? We see it here.
Yes, there's a significant lag at MA of 1 and AR of 1. And I'm just gonna wrap up the lecture because we're like 10 minutes over and I don't want to keep people for
Is
lunch
it
too
good or
much.
bad? Tell me. Like,
It's not a moral statement. It's not like a moral judgment. There's no like good or bad, like, right?
what are the
We get an okay to look at these values and then we say, okay, we want to look at these significant lags. And we start at 0 for our non-seasonal terms. And we say, okay, how many terms are there going to be? There's going to be 1, and then we look at the next one and it says not significant. So we say, okay, just 1 non-seasonal moving average term. Then we look at the seasonal terms. So here I'm seeing if 1, 2, 3 are significant, even 4. And here I see that my 1 is significant, but my 2 is not significant. So I stop and I say, okay, my seasonal moving average term is also 1. Then we'll go to the partial autocorrelation function and we do the same thing, but for our autoregressive section, right? And so we say our not significant. So we have an AR of 1. We then look at the seasonal lags and we say, okay, cool. So from 1 is significant. We look at 2 is not significant. So we say, great, we have a seasonal autoregressive part of order 1. And so to wrap that all together, we have the ARP is 1 for non-seasonal. We only differenced 1 time non-seasonally. And I'm sorry, yes. And then the MAQ is also 1. The moving average is also 1. We did 1 seasonal differencing, and we found 1 significant lag on both graphs for the seasonal terms. And then our S is the period. And so that's essentially saying what our season is. And then we build the exact same thing that we had before. So the only difference here is that there's a couple of more 4s. And also, when we're making the ARIMA model, we do a slightly different syntax. We say the order is equal to the vector, that's, P, D, Q, comma, and then we have to set this seasonal equals list. And so if you ever like, I can't remember, there's documentation, or you can rip it from here. In the list, we also include the order. And the order will be the P seasonal, the seasonal differencing, the Q seasonal, and then you set the period equal to period. This is essentially like using a dictionary kind of in Python in order to pass values to a grid search. It's very similar. So the p-value here, right, same thing. We're taking the p-value of our model after we made it, just the residuals. We'll take the sum squared of errors, and then we cat that all together in order to print it. We'll then look at all the values. That one looks pretty good, but that one looks even better. And so you are essentially just picking the one with the lowest AIC. You can obviously try some of the ones that are close if they are very, very close. But we not only have a good AIC, we also have a decent p-value as well. And so with both those things in mind, we will pick this model. Huh?
If we get any of the good p-value or AIC, which is this model is good.
Yeah, I would say like be cautious about picking like a p-value that's like 0.1 or something, right? Like maybe you should, you know, if all of your p-values are like barely over your significance, then maybe you should be like, I wonder if there's more things for me to look at in the data and trying to fix the data.
The second last is like p-value is 0.79 and USC is like smallest.
The AIC is smaller here. But yeah, it's essentially very close. Typically no in time series data. Typically no. And the question is, with that many for loops, do we have to worry about time complexity? Typically no, because time series data is really small. But if you are, you know, working with large time series data, then yes, it will take longer. And there are many, many great cloud computing services that will help you with very complicated or very costly runs. Cool. So we'll pick this model. And this is just us, you know, making the ARIMA model. This is literally the same line from the for loop, but with all the values written in instead. We can then predict using the forecast command. Forecast takes in the ARIMA model, how many steps forward you would like to go, and then your confidence band. And so the H is essentially just how many steps forward. So in this case, we are predicting 2 years because we're predicting 24 steps forward with 1 month per step.
With a confidence of 80%.
Yeah. With a, you know, a confidence interval around it of 80%. And so we'll plot it, and we get some nice values that are very in line with the rest of our time series. Yeah. And so that's how you implement time series and implement Surima models in R. I'm sorry for going over, but it's a lot of information for one lecture. Yeah, imagine if we did all the derivations. And you can kind of see it here, but we have this kind of like the confidence interval gets wider and wider as we, you know, move further and further out, because there reaches a certain point in which we are essentially saying, right, I'm only using synthetic data. Because if I look at my model, what did my model end up being? My model ended up being 2 seasonal aspects, right? There's there is a seasonal, right, trend that exists, as well as a local trend. My seasonal differencing gets rid of the seasonal differencing. My local differencing gets rid of the local trend as well. So what's left? What's left is just whatever the random noise values are from a year ago and how many people took flights a year ago. And so we kind of have this relationship where if we remove these kind of underlying trends that exist in the data, we're kind of just looking into the past a little bit and adding some noise. And that's part of how you read the time series. I don't want to like keep you guys for too long. But just to go over it officially, capital P is for the seasonal autoregressive model. D is for seasonal differencing, capital D. Capital Q is for the seasonal moving average model. And S is the period of observation, i.e. days, months, years, etc. So, right, if we're looking at months, then the period of observation would be 12. If we're looking at days and we have a bunch of yearly data, you know, the period of observation could be 365, right? We could figure out different ways of cutting up the data. Yeah. This is not super necessary, but essentially this allows us to update our walkthrough to be just a little bit more defined as we do all the same steps to begin with, except for looking also to remove seasonal and local trend. The way that we do that very often is by looking at a small section of the data. For the airline data, I only looked at the first 4 years in order to get an idea of what the trend might be, and if there does exist seasonal trend. Then we do the Leung box test. Leung box test tells us to go, great. We do 4 and 5, which is what we did. We looked at the ACF to determine the order of MAQ and S, the seasonal MA, capital Q. The PACF shows that for the autoregressive and seasonal autoregressive. And then we do the same thing. We check the AIC, sum squared of errors, Leung box Q statistic, and then we predict. And that's it. Thank you guys so much. Yeah, I'm sorry I went so over. I hope you guys have a quick lunch and hopefully not too much to do in the afternoon.
We want to go over how to read the time series just once again.
Yeah, totally. We can in the, yes, cool. So the two things to keep in mind here, right, with the time series is that we did a seasonal differencing and we did a log, right? We did seasonal differencing, we did local differencing, and we took a log. So essentially, those add some kind of implications to what we're doing, right? So because we took the log and we're predicting on log transform data, we know that these trends are kind of continuing to spike and to kind of trough, right? The distance in between these points increases. So the highs are gonna get a little higher and the lows are gonna get a little lower. But since the general trend is upwards, I don't think that these lows a lot of the time will pass very far into, you know, some of these lower areas. However, knowing that we have these seasonal trend as well as the local trend, when we take those aspects out, right, the aspects of essentially things that happen in March plus, you know, some randomness, we can say, hey, if I were to take out all of that stuff and to think about it of just the individual pieces that matter, right? Like what changes, right? How do I predict these new values? The way that we were told, essentially the one that had the best score was the model that builds out Oh, that builds out one moving average part. Sorry, I was rushing to the end of this. One moving average part and one seasonal moving average part. Right? PDQ, yes. Yes. So it's essentially just saying that, you have some kind of random shock from the month ago, right? Maybe there's something affecting air travel, right? That's, sort of bigger than, what's contained inside of our data. We say that that's a factor. It's a local factor, right? Because we're looking at that 1 month before value. And then we're also looking at the seasonal impact too. So we're looking at the random noise from that 1 year before value too. And so we keep all of those things in mind when we are doing these predictions. And essentially what you're saying is, it should behave very similarly year over year, minus some, perturbations, some unexpected things in the market. Yeah, does that clear it up?
For both of them, is there also, does it say anything? Like P value, the PDQ, P is 0 for seasonal and local. Say something?
It doesn't really, so it doesn't say too much because what it's kind of saying implicitly by the differencing is that these values sort of carry ahead seasonally, right? So the change or the shift outside of those purely seasonal or purely local trends happens only via these random perturbations, right? These random shock values, instead of looking historically at, just a raw number of how many flew, right? Of how many people flew on the plane. Right? Because in the autoregressive case, if we were looking at a year ago, we'd be looking at the value of the number of air passengers that flew 1 year prior.
Here that doesn't say anything. That doesn't prediction.
Doesn't contribute anything. Only in the sense that like the differencing, right? There's like some kind of upward and seasonal trend there that's happening that makes the graph do what we saw at the very beginning. Where are you? Right. Because the seasonal part is making it do this fanning out where it's kind of like, it's peaking even higher every time. And then the local trend is fixing the, the like this way. Right? So like it's going up like this. And the seasonal part is like the big peaks. So the local trend makes the line go flat. And then the seasonal differencing makes it makes some of the peaks go away, but the log also helps with that. Cool. Yeah, you guys are totally free to go to lunch at this point. Yeah, I'm here to answer any and all questions because I have a meeting at like 2:30, so I will be sticking around. Cool. What's up?
Sorry to interrupt. I don't think the mic's working.
James, can you hear me?
Yes, now I can. Thank you.
Yeah, hi, James. I'm talking about a real code challenge given by Facebook. So the passing rate is pretty low most of the time, because if you pass this interview, probably they're gonna fly you to Mountain View for onsite. And typically in the bootcamp, we see about 10% people can solve this inside of the class. There was one bootcamp, very overwhelming, 40% of the class solve it, but majority is like 5 to 10%. So it's a good first step into the real code challenge. Usually you will get a Google Doc link or CodePad, and you will see 4 columns being Facebook ID, action ID, type, and referral ID. So when you see a matching between referral ID and action ID, usually it means this is a comment on the original post. This is a share on the original post. So we don't know anything about 4, 3, 4, 5, and 2, 3, 4. So Facebook might have other ways to use the referral ID. But in this case, we care about the post, the comment, the share, the photo, and we have specific task we want you to perform. So the first is a grouping concept. We want to group story and a non-story. So anything is not a comment, consider a story. So a post is a story, a share is a story, a photo is a story, but comment is not story. So based on this criteria, we can say the first transaction, the third transaction, and the fourth transaction are story, but the second transaction is not story. Second thing we have concern about is whether a transaction have a comment or no comment. So with limited record, we can tell the action ID 1001 have 1 comment and 1 share. And when we move to the second record, 982, it has no comment, no share. And 734 have no comment, no share. And action ID 985 have no comment and no share. Is that clear? So one question for you. Action ID 385 is a repost of action ID 1001, but it should be considered as a separate story. We're not chaining it back to its origin. Can you see why it should become a separate story? What's the business indication of this decision? Sorry. Can you speak again?
There can be comments and shares on that particular shared comment.
I see. So one of the students in the class saying it could be more comments and share on this person's post, share. So if you post something and Lady Gaga saw it and repost it, it's gonna have different effect, right? So everyone have your own social circle. The impact of your post is totally different. The impact of your share is totally different. When Facebook tried to calculate how much ads to put into your activity, it's very important to know who you are, who are sharing the voice with you. So out of the business consideration, they should treat each share as separate story. They will have totally different rank on ads, right? So typically you were gonna be given more than 4 records, and you can, like, most likely you're not gonna be asked to generate this dummy data set on the fly because it's gonna take minimum 5 to 10 minutes. You will be asked to write code to solve the problem right away. But afterward, if you want to test your idea, it's a good idea for you to write some dummy data set to test your code, okay? For today's 30 minutes, don't spend time on generating the dummy data set. Okay, so your goal is to output a distribution for comments to each unique story. So for example, right now we have 2 stories. Total, we have 3 stories in those 4 records, right? And there are 2 stories have no comment. And action 1001 have 1 comment. and we only see one story have one comment. That's how those 4 data records get aggregated in this final table. So we care about a sorted table of number of comments ordered from 0 to unlimited number and how many story under that. Once we know this list, it's easy to see which story is going viral and how much percentage of the story have a lot of comments. Then they can engineering all the ads, all the activity there. Does that make sense to you? This aggregation? So the complexity comes with, you need to define what story. You need to aggregate on comments. And most likely, if you have bigger data set, you're gonna see a record like this. This many story have 0 comment, this many story have 6 comment, all the way down to the end. Okay, so you can solve this problem by Python, by R, by SQL, anything. I have seen one student use R and solve this problem by 1 line of code, unheard of. But majority of people would be able to solve it within 20 lines of code. You can do subtable, you can do table join back to its table, anything you can think of. You learn group by, you learn aggregation function. So just pick something you would be interested in implement. Any question? Yep. You are writing the algorithm. You should write the code ready to produce the result. Okay. So you can say you can import this data and what are the steps to take to process, massage the data. So spend your 30 minutes on solving a problem from here to the final output. The other one is take home. So I'm not gonna go over that now. Yeah, so you generate the first column, number of comments, and find how many story have that many comments. So I would recommend you to write out your algorithm first. What's your strategy to tackle this problem? You can use comments like first step, I want to aggregate on something. Second step, I'm gonna aggregate on something. And finally, I reach this. Once you have the key pointer, you can write out your solution. You should have much more data. It's just an example. Yeah, you just assume you saw this, you have it imported in your environment already. Don't spend time to create the data. You need to write the logic from this transactional data to the output. Any question about what you want to accomplish here? All clear? Good. Online student, do you have questions? All clear? Awesome. Good luck. It's your first trial of the real code challenges. I'm not even kidding. If you get this done in 30 minutes, Facebook fly you into their office for onsite. The passing rate is really low. Anything, Python, R, SQL. So at 3 o'clock sharp, if you have the answer, you can email hiring@nycdatascience.com so I can take a look of your result. Okay. Ready, steady, go. It's 2:30. Feel free to Google, feel free to look at any question in the slides.
Hello, everyone. We will be going over the machine learning lab soon. So I guess we could take a break first. We'll go over the lab at 3:10. Oh, where? I don't know for this one. Oh, hiring. Yeah. Vivian will review this tomorrow. I believe you email it to hiring@nycdatascience.com.
Direct message.
Hmm?
I can find.
Oh, not on Slack. Email.
How would I know?
Hold on. Let me ask Vivian.
Time's up. Feel free to submit to me by the, continue to submit till we come back to review the solution.
Is Slack you? I didn't know what to say.
Send me emails, so it's easier to download everyone's solution at once. Also, if you finish the first one, please continue to work on second one. Because they're very, very typical interview question, you should know. Okay, that.